speak here. I will be speaking about generating Sobolev orthogonal polynomials using numerical methods. This is somewhat similar to other projects that I have been involved with. So it was mentioned that I did my PhD in Belgium, and there we did something similar, but for a different type of function, so for orthogonal rational functions. So that's like the first three collaborators, so my two supervisors, and then their current postdoc, Amin. But I will be focusing today more on the Sobolev orthogonal polynomials. So you can see on the last four names, those are people I'm currently collaborating with on Sobolev orthogonal polynomials. So people in Spain, Italy, and Belgium. So you will recognize at least one name, Paco Marcean, I think, on this slide. And so it will be actually the work that we did together, what we collaborated on, will not be the biggest topic here. I will focus on some work, that I also did by myself. So a small overview. What I will do is I will not start immediately with Sobolev orthogonal polynomials because I think people are not, I don't think everybody is familiar with them. So what I will do is I will first start talking about orthogonal polynomials and talking about a connection between orthogonal polynomials, quadrature, and structured matrices. And this will be important later on. So, and then, using these connections, I will show you how you can numerically generate orthogonal polynomials by reformulating this as a matrix problem. This reformulation is interesting because once we have a matrix problem, we can use algorithms which come from numerical linear algebra. And this might have, in some cases, this can have advantages because in numerical linear algebra, there's been a lot of study on the propagation of, for example, rounding error, or also on certain conditioning of certain problems. They're very well studied. And then when we have seen this, and then I hope, these connections are clear, and then we will generalize these connections slightly and show some new results which link some of these things to Sobolev orthogonal polynomials. So I will stress the differences that we have to make between orthogonal polynomials and Sobolev orthogonal polynomials. And then we will numerically generate these Sobolev orthogonal polynomials again by reformulating as a matrix problems, then propose two algorithms, and then we will look at a numerical experiment. So first of all, orthogonal polynomials, and let's look at the connection between three topics. So orthogonal polynomials, to define notation. So we have a space of polynomials P, and when I want to indicate that it's up to degree K, I will denote it by Pk. So for these polynomials, we have an inner product, which is indicated here by these round brackets, PQ, and this will be some integral between A and B. These can be possibly infinite, this A and this B. And then we have the product of these two polynomials and a weight function, Wx. And such a sequence of orthogonal polynomials with respect to this inner product will be a sequence of polynomials Pk, starting from 0. And they have to have exact degree K. So that's the first condition. And the second condition is they have orthonormality with respect to this inner product. So that if you plug in Pk and Pl, you get 0 if K is not equal to L, and 1 if it's equal to L. We take orthonormality because the connection then to these matrix problems, it's a bit more, it links much easier with the more common algorithms that you find in numerical linear algebra for the problems that we will see. Okay, for such a sequence, we have a three-term recurrence relation, and this will be very important in relating the polynomials to matrices. So here we have a three-term recurrence relation with parameters beta and alpha. And here's an expression for these coefficients, but that is not super important at this point. The second topic is quadrature rules. So in this case, we have quadrature nodes and weights, x and w. And what these do is when we start from a integral, so from a to b fx times wx, then we can write this integral as the sum of two parts. The first part being a finite sum over m function evaluations in these quadrature nodes. And the sum is weighted by these weights wj. I use wj square because, well, for all the things we're considering, our weight function, I should have mentioned here, this wx will be positive on the interval ab. And here, again, these weights, we assume that we have a nicely behaved quadrature rule, and so our weights will also be positive. So this is, well, this is just notation, this square. And again, it will be an easier notation as we move forward to the matrix problem. And then the second part on the right-hand side is Rm. So this is the remainder depending on the amount of quadrature nodes that we use, so m, and depending on the function that we plug in into this integral on the left-hand side. The degree of exactness d, well, we say that a certain quadrature rule has degree of exactness d if this remainder is 0 for every f, which is a polynomial of degree d or smaller degree. So for m nodes and weights, we have what is called interpolatory quadrature rules, which have degree of exactness m-1, and we have Gauss quadrature rules, which have degree of exactness 2m-1. And the nice thing, so this is the first connection, for these Gauss quadrature nodes, so if you want to compute these nodes, which we have here on top, these are in fact nothing more than the zeros of Pmx. This is the mth orthogonal polynomial for the inner product, and where we use, for the inner product, we use the same AB as in the integral on top of this slide, the integral of interest, and Wx, the weight function. And then, yeah, the Gauss quadrature weights, you can also retrieve this from the polynomial. So these are the Coates numbers, but I'm not going in detail on those. And then the third topic are recurrence matrices, so structured matrices of some type. So the three-term recurrence relation for orthogonal polynomials can be written as follows. So as we have here. So if we go back to this three-term recurrence, this is for 1, so for the kth degree polynomial. And by multiplying on the left with x, we generate k plus 1. Now, if we group all these polynomials together in a vector, and we multiply by x on the left, then we can rewrite this as the same vector of polynomials and multiplied by a matrix Tm, which is a three-diagonal symmetric Hermitian matrix we have here of size m by m, plus one term plus beta m times Pmx, so generating the next polynomial in line. And here, well, we can verify that the eigenvalues of this matrix Tm are the zeros of Pmx. And the Coates numbers can actually be found as the first components of the eigenvectors. Okay, let's put all of this together. So what we actually have is on the left, these Gauss quadrature rules and their nodes. So the Gauss nodes, they correspond to the zeros of the orthogonal polynomials, which you see on the top of the slide. And if we use the recurrence relation and we plug in the recurrence coefficients into a matrix, we get the recurrence matrix on the right. And we know that the eigenvalues of this one correspond to the zeros of the OP, or orthogonal polynomials. And so the Gauss quadrature nodes are also the eigenvalues of this matrix. So you have kind of a circle in which you can make connections. And this is these are important connections. And there has been, for example, one, I think it's a rather famous algorithm. One famous algorithm for computing Gauss quadrature nodes goes as follows. So this is the Golub-Welsch algorithm, introduced in 1969. I don't have the reference here, but I have it at the end. So here we assume, so this is on top, we assume that computing recurrence coefficients is easy, so efficient in some sense. And the Golub-Welsch algorithm, what it wants to do is it wants to compute the Gauss quadrature rule for some given integral as we have had before. The first step you do is we connect this integral with a inner product, in the sense that we use the same weight, we use the same interval, and we create from this integral of interest, we create an inner product for orthogonal polynomials. And then we know that we can use, that we can compute these coefficients with the expressions that were given a few slides before. And then we can construct this matrix on the right-hand side using these coefficients. And then to obtain the Gauss quadrature rule, we compute the eigenvalue decomposition of this symmetric three-diagonal matrix, which is which is a well-known problem. It's so very good numerical methods exist to compute this eigenvalue decomposition, and so this will give you a reliable, robust algorithm to compute Gauss quadrature rules. However, this is not what we're going to do today. Our assumption will be different. Oh, I should have changed the assumption on top. So the assumption should be that it's easy to find the Gauss quadrature rule. So here in the case that we're studying, we want actually to compute the recurrence coefficients themselves. So what was kind of mentioned before is that, well, in this part, so step 3, is that the eigenvalue decomposition of Tm of this matrix reveals the nodes and weights of our Gauss quadrature rule. And so if we look at, on the bottom of the slide, if you look at the eigenvalue decomposition, so Q star lambda Q, we see that our lambda, our diagonal matrix of eigenvalues, is nothing more than our quadrature nodes x1 through xm. And these weights, wj, they appear in the first column of Q. They are weighted by mu0. This is fine. And you see now why I used the square in this Gauss quadrature rule. Is because in this Q now we just get W1 itself. Okay, here the assumption is correct. So here what we're going to do is we're going to flip it around. We're going to assume that finding a Gauss quadrature rule is easy, but it's difficult to compute the recurrence coefficients. So what we're going to do then is we know that we want a three-diagonal matrix because we know we have orthogonal polynomials. And we want to compute a three-diagonal matrix such that it has a certain eigenvalue decomposition where the nodes are these Gauss quadrature nodes and the eigenvalues are Gauss quadrature nodes, and the weights, so the weights in the quadrature rule, appear in the first column of our Q. And this is called an inverse eigenvalue problem, and this will be the main problem that we will have to solve in this during this presentation. So let me take a step back and let's look at the real problem that we're looking at, and we will see that if we want to numerically generate orthogonal polynomials, we will end up with such a inverse eigenvalue problem. So our goal is given an inner product, same as before. We want to solve the problem of generating an orthogonal polynomial sequence as it was introduced before. The first step that we will do is we're going to discretize the inner product with a Gauss quadrature rule so that we have these nodes xj and these weights wj. And then we want to reformulate this problem that is defined above, so generating orthogonal polynomials, as a matrix problem. And then 3, we solve the matrix problem. All right, so the kind of the missing link to connect the orthogonal polynomials to our matrix problem is, this gap is filled by Krylov subspaces. So this is the definition of the Krylov subspace, which you see above. A Krylov subspace for a matrix A generated with a vector V is this thing right here. So it is a span of V, A times V, A squared times V, and so on until A to the power m minus 1 times V. And this is a very, it's very much used in numerical linear algebra, and there are very good methods which allow you to compute the nested orthonormal basis Qm of this Krylov subspace. So Qm is defined here. So it's Q1 up to Qm, the small q, and it has orthonormal vectors. And we have that it's a nested basis for this Krylov subspace. So we have that the span from Q1 to Qk is equal to the span from V of V, AV up to a to the power k minus 1 V. And you see here that if this Qk is in this span of V, AV, until a to the power k minus 1 V, then this Qk can also be written as a polynomial, pk minus 1, evaluated in A times the vector V. And so this is where the connection between polynomials and matrices will become clear. Yeah, so the two algorithms to compute such a nested orthonormal basis are the Arnoldi iteration, which can be considered to be a modified Gram-Schmidt orthogonalization procedure. It is done in a somewhat smart way, but you can just think of a Gram-Schmidt procedure applied to these vectors that span the Krylov subspace. So then we get some kind of a recurrence relation. So A times Qm equals Qm times H, which is a Hessenberg matrix. So this is a recurrence relation on the basis vectors Q1 up to Qm. If A is Hermitian, then we get the Lanczos iteration. So then it's the same relationship, but now this matrix here is a three-diagonal matrix T. Okay, and so if we go in detail on how to reformulate a matrix, the polynomial problem, into a matrix problem, well, that's what we do right here. So on the left, we have the polynomial problem, so generate a sequence of orthogonal polynomials. And we're going to generate it not for the continuous inner product, but we're going to generate it for the discretized inner product. And we assume that we have, we don't assume, we compute a discretization of this inner product, this continuous inner product, that is exact for all polynomials up to degree m minus 1. So that means if I plug in two polynomials of degree m minus 1 or smaller into my discretized inner product, then I will get the same result as if I would have evaluated it with the continuous inner product. So this can be obtained by a Gauss quadrature rule, for example. And so then on the left, in the problem side still, on the bottom, you see the discretized inner product as we have seen it also before. And what we want to do is we want to connect it to the problem on the right-hand side, which is for now a non-defined matrix problem. However, we know what our result must be. It must be a three-diagonal matrix which contains the recurrence coefficients of these orthogonal polynomials. And we also know what the inner product is on this space. It is the usual Euclidean inner product on two vectors. So V and Y on the right in the problem box on the bottom is the Euclidean inner product of two vectors in Cm, so of size m. And how are we going to make this connection? Well, we're going to use what is on the bottom, just the recurrence relation itself. So here we have the recurrence relation. And of course here, I don't have this extra term plus Pm anymore, because I only have a discretized inner product with m separate nodes. So this means that once I have, m orthogonal polynomials, the next one will vanish for all these inner products. So if we plug in a polynomial of degree m in our inner product, then it will vanish for all the it will vanish for everything. So what we do now is we're going to plug in this bottom, so in our three-term recurrence relation, we're going to plug in x1. So one of the nodes that we have in our discretized inner product. And we're also going to multiply from the left and the right, on the left and on the right with the weight W1. And we can do this also for x2 up to xm, and we put this all in a matrix form. And then we get, well, from our three-term recurrence relation, we can now write as well this, well, matrix factorization in a way on the bottom. So on the left, we have a diagonal matrix, and then here we have two matrices, which we'll call Q. So containing evaluations of our polynomials in the quadrature nodes multiplied with the weights. And we can see that on the left, what we actually have are the eigenvalues of our matrix T, which we plug in on the top. So on top, we now have, so on top in the problem side, we now know a bit more about our matrix problem. We know that we want a factorization of lambda times Q equals Q times T. And this Q, well, you can verify that this is in fact a orthonormal matrix. So if we take our QK, so here in the problem box on top, on the right in the matrix problem part, on the bottom we have QK and QL, of which we take the Euclidean inner product. Now, we know from before, so I will go back a few slides here, now on the bottom, that QK can be written as a polynomial of degree k minus 1 in A times V. And so we'll use this and we'll plug it into our Euclidean inner product here in the first box, the problem box on the bottom. And if we plug in QL and QK, what we get is this row vector times a column vector. And if we multiply this out, what we get is exactly the discretized inner product that we needed to generate our sequence of orthogonal polynomials. So this means that there is a one-to-one connection between the discretized inner product and a well-chosen Krylov subspace, which is, well, so there's a one-to-one connection between the discretized inner products on the polynomials and the Euclidean inner product on these vectors, which come from a Krylov subspace. Okay, there's one thing that needs to be specified as well, and that is these weights. So we need to, in some way, enforce that these weights appear in our matrix Q, and so this is the red condition. So up to a multiplication with a constant C, we need that the first column of Q is equal to the weights that appear in this discretized inner product. And only then will we have this connection between the polynomial inner product and the vector inner product. Okay, so that kind of finalizes how to formulate this matrix problem. So what we will be given is nodes, which are the quadrature nodes, so x1 to xm, and weights, which are the weights which appear also in the quadrature of this continuous inner product. And what we have to solve, what we have to find, is a three-diagonal matrix T and an orthonormal matrix Q, whose first column are the weights that were given to us. And we need that the eigenvalue decomposition of T is Q star lambda Q. All right. So, well, now that we have formulated our matrix problem, we want to solve it. So I will discuss, well, very shortly, one algorithm, so the Lanczos iteration. This, I mentioned before, it generates a orthonormal basis for a Krylov subspace. Here I took a snippet from a very nice book by Liesen and Strakos. I will not go into detail on this one. And well, this approach was first used by De Boer and Golub in 1978. So yeah, Again, so the Lines-Strauss iteration is a form of Gram-Schmidt orthogonalization on the vectors of the Krylov subspace, which I repeat right here. So if we apply this algorithm that is right here, so the Hermitian-Lines-Strauss algorithm, we get as outputs Qm, so a column which forms an orthonormal basis, exactly what we want, and Tm, a recurrence matrix for these orthonormal columns. And we also have that the eigenvalues of lambda are preserved, so T and lambda share the same eigenvalues. However, there's an issue with this iteration, namely it is numerically unstable. So one first solution that you can think of is do reorthogonalization. This means that you do not once Gram-Schmidt orthogonalization, but you do it a second time as well. This does improve the numerical stability a bit, but it also increases the computational cost. But there is another, in this case, a better algorithm, which is, so an alternative, which is numerically stable. And that is the second algorithm I will talk about, so the updating procedure. So this one was first proposed in 1984 by Krach and Harold, and it's based on the following observation for these discretized inner products. So we have this sum from JS1 up to M, and we can just split off one of the terms in our series. So we split it up into a sum from JS1 up to M minus 1, and then this one term right here, just involving the node XM, M. And then we consider them to be two separate inner products. This updating procedure, what it does is we assume that we have the solution for this larger inner product, so for the one from JS1 to M minus 1. And well, if we don't have this solution, we can always keep splitting up until we have just two terms, and then adding one term one by one each term in order to reach M minus 1 terms. So this is without loss of generality. We can assume that we have this solution at hand. And then the problem for the other inner product, which only consists of one term, is kind of trivial. So T hat is nothing more than the node itself, so XM. And then Q has to be unitary, so it has to be the number 1. And so then we immediately get our solution. And now what we're going to do is we're going to take these both solutions and we're going to try to put them together. So add the solution of the smaller problem to the bigger problem, and then in a way update the T twiddle that we have for the bigger inner product and update it with this solution for the smaller inner product. Okay, so this is rather involved, so we're going to take our time to discuss this. And we can generalize this easily to the Sobolev orthogonal polynomials, the idea of it. So it's good that we go over this now. On the left, we have the available solution. So this T twiddle for this larger inner product. And yeah, here we have the formulation of the inverse eigenvalue problem, so our lambda and our weights W. And then we have the solution, the three-diagonal matrix, and then we have the three things that must be satisfied. And on the right, we have our updated solution, so what we want to achieve, that is our lambda is now the lambda twiddle from the left, and, so this should be XM, not XM plus 1. So we add XM on the diagonal together with these other nodes in lambda twiddle. And then for W, we take our W twiddle and we add WM to it. And the updated solution should be, again, a three-diagonal matrix and satisfy these three equations the same as before. Okay, so what are we going to do? We're going to try and get a candidate solution and see what happens. So the first thing that comes to mind is we take our T twiddle, so the solution on the left-hand side, and we're just going to put this XM that we want to include, we're just going to put it on the diagonal of our three-diagonal matrix and see what happens. We notice that for this to, for this to hold, so for the recurrence relation that you see under the satisfied block, for this recurrence relation to hold, we must also increase the size of our Q matrix, and we need it to be unitary, so we add a 1 on its diagonal. And then we get something of this form that you see on the right. So CW twiddle, and right underneath a 0, and all the way at the end, on the right-hand side, on the bottom, we get a 1. So this is a unitary matrix. However, we see that one condition is not satisfied, namely the first column of our new Q is not equal to the wanted weight vector, well, the weight vector that we want, because the last element in our W is Wm, which cannot be 0. Meanwhile, in our newly constructed Q, our last element is a 0. So we have to deal with this, and we have to introduce this weight somehow in our Q. And how we will do this is we will use a plane rotation, also called Gibbons rotation. So that's a unitary matrix. And we denote it by Pij, where I and j indicate where we have these parameters a and b. So that would be on the ith row and column and the jth row and column. So it looks like this. So we only have 2 parameters, a and b, and otherwise this matrix is the identity matrix. And what we can do is, well, we take this newly constructed Q and we multiply it from the right with a plane rotation. And we design this plane rotation in such a way that if we multiply it from the right, then we introduce in the first column, we introduce this Wm that we need to have on the first column. So you can see that one in red. Okay, so that's great. So let's plug this into our scheme. So we multiply with this P1M everywhere. So I put it in blue on the right-hand side. And now what we have is we have satisfied our recurrence relation. We have preserved the orthonormality, the unitarity of our Q, because we have multiplied with these plane rotations, which themselves are unitary. And we have that this first column in our newly created Q, so after this plane rotation multiplication, has the weights that we require. So everything looks good. However, we have to look in our recurrence relation, we have to look at what happened to our T, because it used to be a three-diagonal matrix, and now we multiply from the right and from the left with this plane rotation, which will preserve its eigenvalues, which is good. However, when we look at what the structure becomes, we will see that it is no longer three-diagonal matrix. So here it's in detail. So here on the right, denoted by this under brace and a star, we have this new matrix that represents the recurrence matrix. Well, then the second line is just RT, which is a three-diagonal matrix, and we have one element XM on the lower right corner. And then after we multiplied these two plane rotations inside, we will see that the bottom row fills up, and there appear elements on the bottom row and elements in the last column. Yeah, and this is not what we want. What we want is we want a three-diagonal matrix, so we have to restore this structure. Okay, in here I made some mistakes on the plane rotations, unfortunately. So the first image you see on the top left is our three-diagonal matrix and this one node added, so XM added on the diagonal. Then the next figure is actually P1M times T times P1M star. So that's where we have introduced the weight into our Q, and we have to also change our matrix T in order that our recurrence relation still holds. However, we see that we get this structure right here, the structure also in the previous slide. And what we will do now is we will design plane rotations which get rid of these red elements step by step. So in the first part, we multiply by P2M from the left and P2M star from the right. And then we go on to the third figure, and there you see that these first two red elements have disappeared, but we have created also an extra element on the last row and the last column. And so then we keep doing this, we keep designing these plane rotations in order to get rid of these elements. And then after a few steps, what we see is that we have recovered, again, a three-diagonal matrix. All right. So yeah, we have to multiply with a bunch of these plane rotations. And because we multiply from the left and from the right, and they're unitary, we actually preserve the eigenvalues of our t. So we preserve the eigenvalues that were given before. So we still satisfy all the conditions we have to satisfy. So we have still our recurrence relation now for a new Q. So this new Q, so on the right, on the bottom, this Q also has to be multiplied with these plane rotations. Orthogonality is preserved because we use plane rotations. And as this was not super clear, but as you can see from this one, so since we start eliminating with P2M, we never touch the first column of our Q again. So this means that we have still the weights that we wanted. That algorithm works quite nicely. It is numerically stable, and it is one of the best algorithms if you want to generate orthogonal polynomials. Of course, there's a side note. If you have explicit formulas for your orthogonal polynomials, you should use those. This is more for certain inner products for which these explicit formulas are not available. Okay, and then now we got to Sobolev orthogonal polynomials. I will not give too much information about the Sobolev orthogonal polynomials themselves. For this, I will refer to a recent, 10 years is still recent, I suppose, a recent paper by Marcean, Paco, and Xu. And I will just focus on what changes now as we go from the orthogonal polynomials to these Sobolev orthogonal polynomials. So it's still the same, we're still dealing with polynomials, but now we have a Sobolev inner product. To be precise, a diagonal and sequentially dominated Sobolev inner product. And what you see here in red, so this new inner product, so with round brackets and subscript s to stress that it's a Sobolev inner product, we get a sum over different integrals. And in these integrals, what we get are the derivatives of our functions p and q. So here it says f and g, but this should be p and q. So this means that before we only had the integral over the functions p and q themselves, but now we can also have integrals over the derivatives of our p and q. And then Sobolev orthonormal polynomials are defined in the same way as the orthogonal polynomials, but now with respect to this Sobolev inner product. And maybe one of the main differences is that we no longer have a three-term recurrence relation, but we have, in general, a long recurrence relation. So this means that we have a relationship between xpk, x times pk of px. So relation between the left-hand side and the right-hand side, where on the right-hand side, all polynomials from degree 0 up to k plus 1 occur. Yeah, so if we now put that in the matrix form, so the recurrence matrix, it will no longer be three-diagonal, but it will have extra elements, so it's a Hessenberg matrix. So here in red, I put the extra elements that would appear compared to a three-diagonal matrix. Maybe one mention of an application of which I'm also trying to look into is if they can be used to solve boundary value problems very efficiently. So there are some works. I just took one that I found some time ago. So I took a snippet from this paper, and here in yellow you see that we have an inner product. So this is a a regular inner product, but we have it over u with the accent, so the derivative of u and the derivative of v plus mu times a regular inner product over the function values, the functions themselves. So this would be a Sobolev inner product. And it comes from this boundary value problem that you see in 18. So the second degree ordinary differential equations with boundary conditions. There are very nice works on certain families of differential equations. But yeah, often it has to be done by hand, so you have to derive how to get these recurrence coefficients for the Sobolev orthogonal polynomials, which correspond to this yellow part. And the idea of the tools that we will introduce today is to make this automatic, so that there's an automatic algorithm where you plug in a differential equation and it will solve this differential equation using numerical tools. But that's for the future. Okay, so our approach here in the Sobolev case is very similar to the previous, so to the orthogonal polynomials. What we're going to do is we're going to discretize a continuous inner product using some quadrature rule. So yeah, in general, what we have is this sum over different different derivatives of our f and g, and we will discretize this with some quadrature rules. This can be quite challenging because we have to, the supports of these different integrals might not be the same, so then you have to, do some effort to get quadrature rules which make sense in this linear algebra setting. But today we will focus on nicely behaved Sobolev inner products. Nicely behaved in the sense that the supports will be the same for the different derivatives. And then, the second step is we want to compute the Sobolev orthogonal polynomials not directly for the continuous inner product, but we will do it for this discretized Sobolev inner product. I'll mention already one algorithm that exists, so introduced by Gauchi and Zhang in 1995. It's a discretized Tilches procedure, which is also based on this, on this discretized Sobolev inner product. And today I will talk about the Arnoldi iteration and the updating procedure. And again, as before, so if we have that our discretized Sobolev inner product equals our continuous Sobolev inner product for the degrees k plus l smaller than 2m minus 2, then this suffices to generate the first m Sobolev orthogonal polynomials. Okay, but we're not going to use this general form. We're going to use one specific case of the Gegenbauer Sobolev orthogonal polynomials, so first studied by Althammer in 1962. And here you can see the continuous Sobolev inner product that we will look at today. So this is the Legendre measure on the functions themselves, plus gamma times, and again, the Legendre integral for the derivatives of f and g. And so this very quickly suggests a quadrature rule, the Gauss-Legendre quadrature rule, which discretizes an integral with a Legendre measure accurately up to 2m minus 1. So yeah, the amount of nodes for the Gauss-Legendre rule should be from 1 to m, not n. Okay, and then we apply this Gauss quadrature rule to both the two integrals that appear in our Sobolev inner product, and then we get this discretized Sobolev inner product that you see on the bottom of the slide. And this will be accurate enough to generate the first, up to degree m minus 1 Sobolev orthogonal polynomials for the continuous inner product. And then, yeah, again, so restating our goal, but now for Sobolev orthogonal polynomials. So we are given a Sobolev inner product. We're just going to take our example from this point onward. We want to generate the Sobolev orthogonal polynomial sequence. So step one is discretization, which we just did. And step 2 is we're going to reformulate this problem as a matrix problem. And then step 3 is to solve this matrix problem. Okay, just a reminder. So before we had a diagonal matrix, and if we take our Krylov subspace with lambda, we could perform the Lanczos iteration and generate a matrix Q, which is orthonormal, and the columns of this matrix Q are in fact polynomials in lambda. And then we know that there was this connection between the Euclidean inner product and the inner product on the polynomials. Now, what we have to do is not use a diagonal matrix, but use a Jordan-like matrix, which we have. So I'm just going to take an example, which we have right here. So here you have J, and here you have the repetition of the node x1. And then on the super diagonal, we have this element alpha. And if we take a function of this Jordan matrix, so if we evaluate a function in this matrix, what we get is on the right-hand side. So we evaluate in x1 on the diagonal, so in the x's, x1, x1, x2 on the diagonal. And on the super diagonal, we introduce this term alpha times the derivative of f evaluated in x1. So that's exactly what we need in order to create a connection to Sobolev orthogonal, Sobolev inner products. So yeah, if we then take a Krylov subspace, but now we apply the Arnoldi iteration, we can show that the Euclidean inner product, so QL star QK, can be rewritten as this blue part. So V star times a polynomial in J star times a polynomial in J times V. And if we write this out, we see all the way at the bottom that we get one part, which is our polynomials themselves. So an inner product of our polynomials themselves, and one term in red, which is a term introducing the derivatives of our polynomials. So a Sobolev inner product, in other words. Now, well, in general, so this is a nice result, I think. So if we take J to be a block matrix of these J's, which you see on the right-hand side, so these Jordan-like blocks, and a vector W, then I've proven a theorem which links these vectors V in Krylov subspaces generated with J and W, so these vectors V and Y. So it connects the Euclidean inner product of V and Y with a Sobolev inner product, like a discretized Sobolev inner product, which you see right here. So there's quite some parameters that you can choose. Yeah, it's let's look at it for our example. So remember our example, we're looking at the Gegenbauer-Sobolev inner product. And then we get the corresponding matrix vector pair as J, where we have our, okay, these Z's should be X's on the diagonal, and square root of this parameter lambda on our super diagonal. And then our vector V, it should be 0 and then W1, 0, W2. So you need a 0 in order to not mix derivatives. Okay, so then we arrive at the Hessenberg inverse eigenvalue problem, which again I will state for our example that we are looking at. So suppose we are given the matrix J, as you can see here, and the weight vector W. Now we want to find H and Q such that Q is orthonormal. Its first column contains this weight vector, and H is a Hessenberg matrix. And we need that it has an eigenvalue decomposition, so a Jordan canonical decomposition that looks like this. And just as before, we can use an algorithm called the Arnoldi iteration, so based on these Krylov subspaces, again, I have taken the algorithm from the Liesen and Strakos book. We will not go in detail on this one either. But I do want to note that we cannot use Langevin iteration anymore because this matrix J that we have given is no longer a Hermitian matrix. If we take the transpose, we see that our gamma now appears on the subdiagonal. Okay, all in all, the iteration is a form of Kamm-Schmidt orthogonalization of this space. So this Krylov space is now has 2m elements. So our outputs will also be a matrix Q2m and H2m, so of size 2m by 2m. However, only the m by m leading principal submatrix of this output contains recurrence coefficients for our Sobolev orthogonal polynomials with respect to the continuous Sobolev inner product. Because actually, if we go, okay, on the bottom, there's another mistake. So that should be because XA, XL for the discretized Sobolev inner product is not equal to the continuous Sobolev inner product for K plus L larger or equal to M. So this means that we lose the connection between the discretized and the continuous inner product if we go too far. So we have to select only the leading principal submatrix of H2M. Well, I'm kind of running out of time, but I will quickly go over the updating. Well, in this case, the idea as before is the same. However, we're not adding one node, but we're adding a block in this case. So in our example, it's 2 by 2. So if we have our Legendre measure, we have already 2 terms, and we want to add one more term. So here we have 2 terms, 2 nodes in our discretized inner product. And for our new inner product, we want to add 1 term, which you see in red. Well, then we need to add, well, we need to merge this 2 by 2 block. So here we have the solution H hat 2 and Q hat 2 as well. And we want to merge these solutions to the already computed Q4 and H4. Well, again, when we naively put these blocks, these solutions inside of our inside of the other solution that we had, the largest solution, then again our first column does not contain the right weights, so we multiply with these plane rotations in order to introduce these weights. However, the structure of our recurrence matrix will change. So this is on the left you see the merged state, so where we just put the solution on the diagonal, and then after introducing the weight vector, we see that we get some disturbance of the Hessenberg structure. And then we keep multiplying with plane rotations until we have restored on the right lower corner our Hessenberg matrix. Two Hessenberg structure. And yeah, here in red you see the recurrence coefficients that we were looking for, so that correspond to the continuous inner product. The rest of the elements, so the elements denoted by these x's, they're actually not needed, but we need to compute with them a little bit. So we can do more efficient by truncating at certain steps, but we'll have to do a bit more work in order compared to the orthogonal polynomials themselves. Okay, so this is a summary of the numerical procedures, but I just want to note that the updating procedure requires fewer memory than the other procedures that were mentioned. One small numerical example, and then I finish. So here we see, well, we're going to compute the roots of these Gegenbauer-Sobolev polynomials, which we were talking about the whole time. And we know that they are simple, real, and inside -1, 1. Now we compute this by taking the eigenvalue decomposition of 4 different Hessenberg matrices. Well, they're different in the sense that they're computed with different algorithms. On the left side, you see in blue and in green, 2 methods proposed by Gauci and Zhang. And on the right-hand side, you can see the two methods that I have discussed today, so the Arnoldi and the updating procedure. And you see that on the left, well, we get complex valued eigenvalues, which is according to, well, the theory is wrong. So the question is, why are these different? Well, it's actually not that the methods by Gauthier and Zhang are incorrect. It is that they compute the recurrence matrix for the monic Sobolev orthogonal polynomials, while I do it for the orthonormal Sobolev orthogonal polynomials. And if we look at the conditioning of the eigenvalues of the monic recurrence matrix, we see that the condition number lies between 10 to the plus 13 and 10 to the plus 16. So this implies that we expect an error of 10 to the minus 2 on our computed eigenvalues when we compute the eigenvalues of this monic Hessenberg matrix, which kind of corresponds, as you see on the left, with the size of, well, the deviation into the complex plane. While if you take the orthonormal recurrence matrix, the conditioning is lower than 1,000. So the expected error is much lower as well. Of course, this is not a problem of the way you compute the recurrences. This is just a problem for the eigenvalue problem itself. So in fact, if you take the monic Hessenberg matrix, you can balance it by multiplying from the left and the right with d and d minus 1, so a diagonal matrix, and you can balance this problem, and then you can compute the eigenvalues as accurately. So here, then we would have on the left side the same as we see on the right-hand side. But balancing eigenvalue problems is a study in itself, so even when we have the recurrence matrix, it's not so simple to compute the zeros of Sobolev orthogonal polynomials, and we have one recent publication which focuses on this balancing problem itself. Okay, well, I will not go over the recap. I'll just mention that for future work, so when you have a Sobolev inner product with specific properties, for example, if there are coherent pairs in your Sobolev inner product, then you can develop specialized approaches where you, for example, can get a explicit formula for your coefficients, which in general works better than this general approach that I have outlined today. And then, yeah, differential equation solvers is also something I would like to work on. Okay, thank you.